Okay, in this last hour for today, we are going to solve a few questions related to conditional expectation. This first question, though it seems a little hard, it's a very basic question for us to understand how we can calculate the conditional expectations, or how we can calculate expectations by conditioning. So the question says that, so I need to make this full screen. The question says that in order to perform a certain task, Pam invites two of her friends who are independently likely to respond to this invitation with probability 0.5. Okay, so Pam is inviting two friends, James and Dwight. So James is going to participate in this invitation with 0.5 probability, and Dwight is independent of James, is going to participate in that invitation with again 0.5 probability. So this part of the question tells us this. So there is a certain task here that is needed to be performed, and Pam is inviting two more people to perform this task. So altogether, either they are going to altogether perform this task by three people, or maybe one of these guests is going to participate and the other not is going to come. So in that case, Pam and another person here is going to perform that task. So this means two people can perform that task, or both of the invitations can be responded with a negative answer. So this means Pam is going to perform that task by herself. Okay, so there are three different situations here. Either Pam is going to perform this task by herself, or Pam and plus one guest is going to arrive and they are going to together, so two people is going to perform that task, or both of the invitations can be responded positively, which means together all three people can perform this task. So basically, the number of people that is going to perform this task is going to be 1 or 2 or 3. Okay? The hourly completion time of the task is exponentially distributed with rate parameter lambda, it says. So when we intend to perform this task, the hourly completion time of this task is going to be exponentially distributed with rate parameter lambda, but lambda is equal to another random variable, y. Y is the number of people, including Pam, who is there to perform the task. Which means, which means the time to perform this task, the hourly completion time to perform this task, is exponentially distributed with rate parameter lambda being equal to 1 if nobody arrives but Pam does this task by herself. Okay, Pam performs this task by herself. If Pam invites these two people and only one of them arrives, in that case, the hourly completion time is going to be exponentially distributed with rate parameter lambda equal to 2. And if both of the guests arrive, in that case, the hourly completion time of this task will be exponentially distributed with rate parameter lambda equal to 3. So you see, the hourly completion time of the task is a random variable. However, its parameter lambda is also another random variable, which is the total number of people involving in this task, who is there to perform the task. So the question is basically asking me this: compute the expected time to complete this task. What is the expected time to finish to complete this task? Now, first of all, we want to determine the possible values of y with the respective probabilities that it can take. Now, what is the probability that none of these two guys is going to arrive? None of them. So James is not going to participate with 0.5 probability, and Dwight is not going to participate independent again with 0.5 probability, which means the probability that neither James nor Dwight responds is 0.25 as a joint probability. So in that case, the number of people who is there to perform the task is just going to be 1, which is only Pam herself. Okay, so with 0.25 probability, neither James nor Dwight will come, and y is going to be equal to 1. And again, with 0.25 probability, again, James will participate with 0.5 probability, and independently, Dwight will participate with 0.5 probability. So 0.5 times 0.5, we have 0.5 because it is said that these events are independent, whether James and Dwight will come or not. They are independent from each other. So both James and Dwight will participate with 0.25 probability, which means in that case, the number of people who are there to complete the task will be 3. And 0.50 probability, exactly one of them will come. So how do you determine this? You know the binomial distribution, right? So here we are inviting 2 people, each of which is likely to arrive with 0.5 probability. Actually, the number of people who arrives among these James and Dwight is a binomial random variable with size parameter 2 and success probability equal to 0.5, and the probability of exact people arriving is going to be 0.50, which means if 1 people arrives along with Pam, there will be 2 people there to perform that task. So the number of people who are there to perform this task is a random variable y, taking on values 1, 2, and 3, respectively, with probability 0.25, 0.50, and 0.12. This is the marginal distribution of y. Now, random variable y is also defining the rate parameter of the exponential distribution, which defines the hourly completion time of the task. Okay, and let's just say x is the time to complete the task. If I know at this point, if I know how many people will be involved in the task, I can easily predict the expected value of x, but I do not know how many people will arrive after this invitation. Therefore, the distribution of x is dependent on the number of people who will arrive, the number of people who are there to perform this task. So because of that reason, x does not have a known distribution. However, the question is not asking the distribution of x, it is basically asking the expected value of x. And in order to calculate that expected value, I am going to use the conditional expectation formulation. Okay. Now, in this conditional expectation formulation, instead we have the expected value of x given y. So x is conditioned on the number of people who are there. And x given y is exponentially distributed with rate parameter lambda equal to 1. So x given y, the conditional distribution of the completion time of this task on the number of people who are there to perform this task is exponential with rate parameter equal to y. And the conditional expectation of x given y should be 1 over y in that case. You know, the expected value of exponential random variable is 1 over lambda. If lambda is equal to random variable y, in that case, that conditional expectation will be 1 over y as well. As you can see, that interior expectation is a function of random variable y. So depending on random variable y, it is going to be different values. For example, if y is equal to 1, which means neither James nor Dwight arrives there to help Pam. In that case, Pam is going to involve in the task by herself, and the average time to perform this task will be 1 over 1, which means 1 hour. But if there are 2 people there, if y is equal to 2, then it is going to be 1 over 2, which means half an hour. If there are 3 people there, then y is going to be 3. In that case, the average time to perform this task is going to be 20 minutes. Okay? So expected value of x given y is 1 over y, as you can see. Therefore, according to this conditional expectation formulation, I am actually calculating the expected, in the outer expectation, I am calculating the expected value of 1 over y. And 1 over y is equal to either 1 or 1 over 2 hours or 1 over 3 hours, respectively with the marginal probabilities of y being equal to 1, 2, and 3. So I multiply the probability of no one will arrive times the average time to perform this task, which is 1 hour, plus 0.50 times 1 over 2. So number of people there to perform task is equal to 2 with this probability, and the average time will be 1 over 2 in that case. And then I multiply the probability of 2 of the guests will be arriving with the probability 1 over 3, which is, I'm sorry, with the average time. 1 over 3 is not probability, it's the average time to perform this task. So we calculate the ultimate expectation of the average time to complete the task, which is 0.5833 hours. Okay, so the question here is question number 7. And this question number 7 is a well-known question which you can find in your textbook. It says, a miner is trapped in a mine containing 3 doors. The first door leads to a tunnel that takes him to safety 2 hours of travel. The second door leads to a tunnel that returns him to the mine after 3 hours of travel. The third door leads to a tunnel that returns him to the mine after 5 hours. So there are 3 doors in front of you. If you choose one door, that door is going to be the correct door, and it is going to bring you safety after 2 hours. So it takes 2 hours to bring you to the safety. The second door leads to a tunnel that returns you to the mine, to the beginning again, okay? And after a travel of 3 hours, and the third door is going to return you, it is going to return you to mine after 5 hours, okay? Now, assuming that, if we read the next part of the question, assuming that the miner is at all times equally likely to choose any one of the doors, what is the expected length of time until the miner reaches safety? The question is asking me this. Now, my friends, you see, after, if the miner chooses an incorrect door, a wrong door, then he is going to travel in the mine for an amount of time, and he is going to come back to the same point. But at that time, when he comes back there, he is not going to remember which door he selected. Because of that reason, we are assuming that every time he comes back to the starting point, he is equally likely to choose any one of the doors. So he can, for example, select the same door again. If, for example, he selects the wrong doors and, for example, travels 5 hours in the mine, after coming back, he can select that door again with the same chance, 1 over 3. Every time he chooses a door, the chances are 33%. So the question is here is this: what is the expected length of time until the miner reaches safety? Now, in order to solve this question, we are going to write down the random variable x as the time until the miner reaches safety. Okay, so that is x, and we are interested in calculating the expected value of x, expected value until the miner reaches safety. And y is going to be the door that he chooses, because his first choice is the doors, right? So when he starts this game, for example, he is going to choose one of the doors. And let's just say y is the door that he chooses, and even though the miner does not know which door is correct door or which door is not, we know that door number 1 is the correct door, and doors number 2 and number 3 are the incorrect doors. When you choose door 2, you are going to travel for 2 hours and come back to the starting point. And when you choose door number 3, you are going to travel for 5 hours and you are going to come back to the starting point again. Okay, so we are going to use the conditional expectation formula here, and we are going to condition that time until reaching safety to the choice of the door. And what happens if we choose the first door in the first selection or the second door in the third door? We are going to calculate these conditional expectations. Then we are going to calculate the expectation of these conditional expectations and reach the ultimate result. You know, if the miner chooses the first door, the choice will be made with 1/3 probability. Just like that, he can select the second door and third door with 1/3 probability. So the probability mass values of Y to take on these values are equally likely, 1/3. Now let's calculate that conditional expectation. What is the expected time until the miner reaches safety? Given that he selects the first door, now we know the answer. It is 2, the expected time, because it is deterministic. If he can choose the correct door in his first choice, then it is just going to take 2 hours of travel, and that's it. He's going to reach to safety. So the conditional expectation of x given y being equal to 1 is just 2 hours. But what is the conditional expectation of the time until reaching safety if he selects the second door? Now, if he selects the second door, he is going to travel for 3 hours, and he's just going to waste these 3 hours and come back starting point. And when he comes back to the starting point, the expected remaining time until he reaches safety after these 3 hours of travel is going to be the same as the expected time in the beginning. Why? Because he is basically restarting the process itself from the beginning. He's going to start the game. After 3 hours of time, he's going to waste 3 hours in traveling the mine, okay? And then he's going to come back to the starting point, and because he does not remember which door he selected, he is going to, the expected remaining time is going to be the same as the expected time that we are going to be looking for. And in the third case, if he chooses the third door, this time he's going to travel for 5 hours, and this 5 hours is going to be wasted. And after that, when he comes back to the starting point again, the expected remaining time is going to be the same as expected value of x. So the process is going to restart itself again. Now, we can run this conditional expectation formula, which means we are going to multiply these conditional expectations with the respective probabilities and sum them up. So the output expectation is conditioning. The output expectation is calculating the conditional expected value of the conditional expectation values here with respect to the probability mass values of y. So we basically say that the probability that he chooses the first door times the expected time until he reaches safety, given that he selects the first door, plus the probability that the miner selects the second door times the expected time until he reaches the safety, given that he selects the second door, plus the probability that he chooses the third door times the conditional expectation of time until he reaches safety, given that he selects the third door. And since we know these probabilities and these conditional expectations, we write 1/3 times 2 plus 1/3 times 3 plus expectation x plus 1/3 times 5 plus expectation x, and that is going to be 10/3 plus 2/3 expectation of x. And you see, our objective was to calculate expected value of x. We are calculating that expected value, but it is, in this formulation, it is given as a function of itself. So we are basically representing expected value of x with itself. But I mean, this forms an equation with only a single unknown, and that single unknown is expected value of x. You can simply solve expected value of x from that equation. If expected value of x is equal to 10, then this equation will hold. Means the time until this miner reaches safety is equal to the expected time the miner until reaches the safety is equal to 10 hours. Okay, so on the average, the miner needs to travel for 10 hours so he can reach the safety. This is the average value. Sometimes, I mean, if for example you put yourself in that position, in that mine, maybe you are going to spend even more time than 10 hours. Maybe you are going to choose the correct door by chance in your first choice, and you are just going to leave in 2 hours. But on the average, if we make this experiment on a very, very large number of people, on the average, we are going to see that the people are going to travel for 10 hours on the average to come outside. Okay, some people are going to be very unlucky. Maybe they are going to travel very, very, very long amount of time until they choose the correct or advanced choice. Okay. So this is a famous question which is explained in your textbook. Again, if you do not understand this question, my friends, I recommend you to study that question. Reading the explanation in your textbook, in Ross's textbook, maybe he can teach you better than me. Now I am going to solve you another question. This time it is going to be a little more complicated. Again, we are going to use the conditional expectation formula. It says we are going to perform penalty shots until we score 2 consecutive goals. We are going to perform penalty shots until we score 2 consecutive goals, which means we need to score 2 times in sequence to finish. Okay? I'm not going to stop when I score 2 goals. I am going to stop if last 2 penalty shots are consecutively scored. Okay? If my last 2 penalty shots are consecutively scored, then I'm going to stop. Okay? For example, you have scored in the beginning. Okay, in shot you have scored. In the second shot, you have missed. In the third shot, you have scored again. Are you going to stop? No. We are not going to stop when we score 2 goals. We are going to stop if my last 2 penalty shots are scored. Okay? So this is the condition of stopping criterion. In each penalty shot independently, we are likely to score with 0.5 probability. So my chance to score in a penalty shot is 0.5, and I can also miss with the remaining probability 0.5. So the question is this: what is the expected number of penalty shots we need to perform? The expected number of penalty shots we need to perform. So the question is asking me the average number of penalty shots that we need to perform. In fact, we can solve this question simulation, but you are going to learn about this in your future courses, simulation courses. I am going to solve this question to you in another way. I'm going to use the conditional expectation formulation. Okay? Now let's just say here the random variable for which we would like to calculate the expectation is n. N here is the number of penalty shots we perform until we stop. Okay? N here is not a geometric random variable. It is not a negative binomial random variable as well. We do not know the distribution of n here. We have not learned anything about its distribution before. Maybe you may think that it looks like geometric or negative binomial distribution, but it is not, because the stopping criterion requires the last 2 penalty shots to be. Okay. So we want to compute the expected value of n, and we are going to condition it on our first operation. What is our first operation? First operation is the first penalty shot, right? So the first shot can either be a score or it may not be a score. So I am going to denote the outcome of my first shot as x1. So x1 is the result of the first penalty shot, and x1 is going to be equal to 1 if my first shot is a score. X1 is going to be equal to 0 if my first shot is not a score, if I miss my first shot. Okay? So the outcome of the first shot is x1. It is a Bernoulli random variable which takes the value of 1 with 0.5 probability, and it takes the value of 0 again with the failure probability 0.5. Now I am going to calculate the expected value of n. So this is my ultimate result. I would like to calculate the expected value of n, and that expected value will be a conditional expectation of n given the first shot, and we are going to calculate the outer expectation based on the probabilities of x1. So we are expanding that. expectation of n by conditioning it on the first outcome of the first penalty shot, which is going to be probability of x1 being equal to 0 times the expected value of n given that x1 is equal to 0. So we basically say that the probability of my first penalty shot is a miss times, given that my first penalty shot is a miss, the total number of penalty shots I need, the expected number of total number of shots I need to perform, plus probability of x1 being equal to 1 times expected value of n given x1 being equal to 1, which means the probability of my first shot is a score times the expected value of the number of penalty shots I need to perform, given that my first score is 1. Kısacası arkadaşlar, ben diyorum ki toplam yapacağım atış sayısını ilk atışımı koşullandırıyorum. Diyorum ki ilk atışımın gol olmama olasılığı çarpı ilk atışım gol olmadığı takdirdeki toplam yapacağım atış sayısının ortalama değeri artı ilk atışımın gol olma olasılığı çarpı ilk atışımın gol olduğu takdirdeki toplam yapacağım atış sayısının beklenen değeri. Yani bu beklenen değeri ilk atışımın sonuçlarına koşullandırıyorum. İlk atışımın sonuçlarının varsayımına göre beklenen değerleri hesaplayacağım. Bunları da ilk atışımın olasılıklarıyla çarpıp toplayacağım. Şimdi ilk atışımın gol olmama olasılığı 0.5, gol olma olasılığı da 0.5. Bunları biliyoruz. I know that the probability that I miss or I score in my first shot is they are both 0.5. So let's calculate that expected value. What is the expected value of n given that x1 is equal to 0? So you miss in your first shot. What is the expected value of n? Now, if you miss your first shot, it is not going to be counted as a progress, right? So if you miss your first shot, this is not going to contribute anything in your progress. If you miss your first shot, now the remaining trials are going to be the same as the trials that you are starting for the first time. Imagine now you have missed your first shot. This is like you are starting the process itself again from the scratch. So until stopping after that miss shot, okay, after that failure in your first trial, the expected number of the remaining shots until you score 2 consecutive goals is still going to be expected value of n. But you have already used 1 shot already. So the expected value of n, given that you have missed in your first shot, is 1 plus the expected value of n. So you have missed your first shot. The process has restarted itself. You have not counted any progress. So therefore, the expected number of the remaining shots that you need to perform is still expected value of n. Okay. Now this is the conditional expectation given that you miss your first shot. Now what happens if you score your first shot? If you score your first shot, my friends, then the expected value of n, given that x1 is equal to 1, is going to be computed by conditioning it on the second shot. Because if you score your first shot, now you can either stop penalty shots in the next shot if you score that too, but if you miss your second shot, you are going to restart from the beginning, right? Because you need 2 consecutive goals. So we are going to condition that second conditional expectation to another random variable, which is x2, the Bernoulli random variable, which is the outcome of my second shot. And x2 is also independently Bernoulli distributed with probability 0.5, and the expected value of n, given that x1 is equal to 1, is going to be expanded by conditioning it to the second random variable. We are just going to say that probability of x2 being equal to 0 times conditional expectation of n, given that x1 is equal to 1 and x2 is equal to 0. So remember, in this conditional expectation, there is already a condition. That condition is going to remain in every part of this conditioning again, but we are also conditioning that random variable in the second outcome. So x2 is going to be equal to 0, and in the second condition, x2 is going to be equal to 1. So I am just going to read this expansion like this. The probability of my second shot is a miss times the conditional number of expected number of the conditional expectation of the number of shots that I need to perform, given that I score in my first shot but I miss in my second shot, plus the probability of my second shot is a score times the conditional expectation of the number of shots I need to take, given that my first shot is a score and my second shot is also a score. Now, I know that the probabilities on my second shot are also 0.5 and 0.5. Now, let's check the first conditional expectation. You have scored your first shot, but you have missed your second shot. So you have taken 2 penalty shots, but you have not counted any progress, which means from this point after the second shot, the expected number of remaining shots until you score 2 consecutive goals is still going to be equal to expected value of n. Imagine now you are restarting the process because the previous 2 penalty shots have not counted to anything. But if you score both of your first and second shots, then the expected number of shots is just going to be 2 because you will be done, you will be finished. So you are basically stopping that at that point. So the conditional expectation of n, given that your first shot is equal to a score, is conditioned on the second shot, and after this expansion, you get to calculate that conditional expectation is equal to 2 plus 0.5 times expected value of n. And that expected value of n here in this first formulation is going to be equal to that formula. And in that formula, we are going to plug in expected value of n given that x1 is equal to 1, which is here. So I am just going to plug in that part to here. And ultimately, I am going to get expected value of n equal to 0.75 expected value of n. And in that equation with a single unknown, expected value of n is going to be 6. Okay, so basically, the average number of penalty shots we need to perform to score 2 consecutive goals is equal to 6. Okay, so if you, for example, if your chance to score and miss every time you take a penalty shot is 0.50, if you are going to stop until you score 2 consecutive goals, then the average number of shots you need to take is 6.